So today, I'm going to put more structures on groups. And I'm going to introduce these structures. Finally, I want to get to what it is to be a harmonic function, and I'm going to introduce the structures that I want to put. So what at the end of the day, what we want to have a group. We want to have a group. So we're going to have a group G. Okay, so what does a group have? So a group that's already a structure, right? It's an algebraic structure. So this is algebra. Right? The algebra, this is the multiplication table. Right? So you have an algebra, you have something, right? You have a list, which is telling you if you take two elements, you get a third element, right? So that's algebra. Then, so that's that's structure number one. Structure number two, that we already saw, is that we have probability measure. We can put probability measure on the group, right? So we can take mu, the probability of G, right? And then we can, and then we have random walk, right? Random walk, we already saw hints about what happens when you have a random walk. When you have a random walk, you have an analytic structure. So this is probability, which is I would call it analysis, right? Of an analytic structure, okay? Right? We already saw hints that we have real analysis going on here, right? Because I told you about the Laplacian and the green function, right? So, and today we're going to do more analysis. We're going to do what I call discrete analysis, or a brief introduction to some of discrete analysis, not everything. You can look in my book, and you can look in other books about how to do analysis on these discrete structures. And the third structure that we're going to have is a geometric structure. So we're going to put geometry. Okay? And geometry comes from putting a metric on the graph. We're going to put very simple metric. These are countable spaces. Just going to tell you what the distance between 2 points is. Then you can take the shortest path. And if I tell you the distance between every 2 points, it defines a metric because you just go over all possible sequences, starting finite sequences from X to Y. You sum the lengths of these pairs, right? And the minimal length is the metric. So
between any 2 points, between generate.
Yeah, so you have to have a notion of neighbors. Neighbors have a distance between them, right? And a path is a sequence of neighbors, and a finite sequence of a finite path. And you go over all finite paths from X to Y, take the minimal length one, and that gives you a metric. That's a generic way to define a metric, honestly. Not every metric is obtained this way, but maybe every geodesic metric is obtained this way. Of course, not every metric is obtained this way because there are metrics which are not geodesic, but this defines a metric, okay? And those are the metrics we're going to use. And basically, it's a graph structure. It's a graph structure, but we can change the length of the edges. That's basically it. Okay, so here, if we have a group, well, basically, we're going to put a Cayley graph. Okay, so even the distance between two neighbors is just going to be 1. Okay, but you could imagine that we do some stranger things, and the theory would still work, but this is basically the structure we're going to, right? So we have a metric. When we have a Cayley graph, you just have a distance between any two graph distance, okay? And that's geometry. So we want to do this. We've done. Okay, this we started doing, and I hope to finish at least introducing the structures we work with today. So let's start with the geometry. So geometry, and I already defined this, but let's repeat the definition. So definition, the network is a pair GC, where G is a countable set. You can ask me what to do in uncountable sets. I don't want to go. So for me, networks only being countable sets. Countable set, and C is a function from G times G to the non-negative real numbers. So it's a non-negative function. It satisfies that it's symmetric. Okay, symmetric. So C is called the conductance. That's why it's C. So the conductance from X to Y is the same as the conductance from Y to X. I already told you, just think of width of a pipe. You're putting a pipe between X and Y, water can flow through it, it can flow both directions the same way. The capacity of the pipe is the same. And so this is one condition. And the second condition is that if you define C sub X to be the sum over all Y of Cxy, then this has to be positive and finite. Okay, so positive just tells you there's at least one guy coming out of X. The finite tells you that this thing is finite. And so you don't have infinite capacity coming out of X. If you pour in some water into X, then X can't hold or can't get an inflow of infinite amount of water. There's no room. You can push in a finite amount of water. Okay? But it doesn't mean that the number of neighbors of X, those that have positive conductance between them, it doesn't mean that there's the finite number of them. It just means that the conductance becomes smaller and smaller rapidly enough so that this thing sums. It could be a different sum for every Cx. Okay? And we're going to talk about connected networks. So what is a connected network? Well, one way to talk about a connected network is to talk about how to get from one point to another point, right? But it's equivalent. We already had an analytic structure applied to this geometry. The analytic structure, so a network, so a remark, a network, GC, induces a Markov chain, which we call the random walk. GC. Okay? And this random walk is just a random motion of a guy sitting at some state and jumping to a new state with probability proportional to the conductance. Okay? So we call the random walk on GC, and this Markov chain has, or is defined by transition matrix. All I need to give you is the transition matrix, right? Right? Because to understand Markov chain, you need transition matrix, and then for every starting distribution, you get some process. So it has a transition matrix, which is given by Pxy. And this depends inherently. So P depends inherently on G and C. Okay, so you have to remember this data that you have. And it's just the conductance, but normalized to be a probability measure divided by C of X. And so you see, it was important that C of X is positive, right? If I had a C of X which was 0, then of course I wouldn't be able to talk about the state X. Okay, and I mean basically this is.
You also need some measure start with.
Yeah, so for every measure, once you have transition matrix, you have Markov chain, and every starting measure gives you a different probability measure on the space of sequences. So this is the induced random walk, or the random walk on the network. Okay. For example, a simple random walk on a graph. So what is a graph? A graph is also a network where each pair of neighbors has conductance 1. And a simple random walk just move 1 over the degree, right? Because this would be the degree, and you get 1 over the degree to a neighbor, right? So you uniformly choose a neighbor. But of course, you can imagine that you put different types, different weights. So maybe it's more likely to go this direction and less likely to go in that direction. So you could imagine many, many different things. And yeah, so we have this. And I don't want to say about the analytic structure. I don't even. Okay. So that's the definition of a network. Oh, of course. Definition: a network. A network, BC, is connected if we just say a network is GC is connected if the corresponding random walk P is irreducible. Remember, irreducible just means that in the Markov chain, from any starting point x and any y, there is a positive probability at some number of steps to get from x to y. There exists a t such that p, t, x, y is positive, right? So this is, let me write this, for every, i.e. for every x, y, this t such that p, t, x, y is strictly positive. Now, exercise, I mean, you can think of it as very easy exercise. Okay, so that a network GC is connected if and only if for any xy there exists finite path from x to y. Okay? What is a finite path from x to y? So there exists finite path from x to y. What is this? I'm going to define what this means, a finite path. That is, what is a finite path? There exists a sequence x0 is x, x1, xn is y. There is some n, okay, I didn't say what n is, but there is some finite number of vertices or number of sites in my set G, such that C of xj plus 1 is always positive, and this is for every j that goes from 0 strictly less than n. So if you look at neighbors, right, this defines a neighboring relation, right? X and y are neighbors if the conductance between them is strictly positive. So you can find a way of going from x0 to x1 and from x1 to x2, positive conductance. So if I push water into x, then it'll start going through the pipes and some water will at some point reach y. Because there's a sequence of pipes with a non-zero thickness to them, right? Non-zero diameter. So you can have water flowing from x to y, and this is for any x and y. And I understand why it's connected. I want you to notice, I mean, and if you have a path from x to y, you also have a path from y to x because of the symmetry of this. Here, it's less clear that you have the symmetry. But these networks, symmetric, and in fact, this n is connected to the t that you find there, right? And you see that you can get the same t from x to y and same from y to x, although not true in general Markov chain, irreducible Markov chains is the same t in both directions. But here, there is some symmetry. There is some way, in some sense, this random walk is undirected. It is actually directed. It's not true that the probability to go from x to y is the same as the probability to go from y to x, because cx and cy could be different. But there is some way of there's some way of understanding that this thing is symmetric in a certain way, okay? Reversible in a certain way. And we'll come back to that point. You'll see that things are symmetric. Okay, so already there is some symmetry. More specific example, if I go back to the group, remember we had an example of a network. Example, if we take a probability measure, group G, right? And so we say that U is symmetric if, the definition, if mu charges x and x minus 1 with the same mass, or any element. Any element and its inverse get the same mass. Okay? This is called symmetric. Then, once we have this, when we have this structure of a symmetric measure, we can define Cxy to be mu of x minus 1y. And because mu is symmetric, this defines a conductance. Okay? And this defines a conductance. So it gives me a network. A network denoted by, so we will always use G mu. For symmetric mu, we will use G mu to denote the network. Mu induces a conductance. It's a special case. A special case. You can check easily that what is Cx in this case? One. I sum over all the y's here for a given x, and I'm just summing over all the group elements. Just getting one. There's some uniformity here. This is equivalent to the network is like a generalization of a graph. This is a kind of a generalization of a regular graph. Okay? All the rows kind of sum to the same thing. So Cx is 1 for every x. Okay? And so you get that the induced random walk is just the same as Cxy, which is, so the probability to go from x to y is just mu of x minus 1y. It's just the element that you need to multiply by taking it from x to y. Okay? And we discussed that, so that gives us random walk on a group. But then, so another exercise for you to look at is that G mu is connected. Again, and if I write G mu, I mean mu is symmetric because there's no meaning to write G mu. I mean, it's not a network if mu is not symmetric. G mu is connected if and only if mu generates G. Okay, so what does mu generate G? So let me write, I'm going to write mu is adapted. Okay. What does adapted mean? Definition basically means that the probability measure mu doesn't live on a smaller group. So it really sees the whole group G. Okay? You can always have mu living on, suppose inside your group G you have some element, and you take mu to be, 1/2 on that element and its inverse. Then mu doesn't see the whole group because it lives just on the cyclic subgroup generated by that element, only on the powers. Right? It can't really know that there are other elements. It doesn't really see them ever. So mu being adapted, mu is adapted. Probability measure on group G is adapted if the support of mu. What is the support of mu? This is the set of all elements in G such that mu gives them positive mass. This is the support. And I'm going to write generates G. So do you know, and you can protest and say, does it generate G as a group or as a semi-group? But mu is symmetric, so it doesn't matter. Okay? So do you know what generates G is? A group being generated by a set of elements, just any element in G can be written as a finite product of elements from this set. Okay? I didn't say it was finite, it could be infinite. Right? You could have mu, which is supported in the whole group. It's possible. Okay? It definitely generates, okay? But there is no problem in what I mean by generates. When you go to non-symmetric measures, and some people look at these things, I don't know why, but they do. So when you go to, no, there is a reason, but anyway. When you go to non-symmetric measures, then you have to be careful what you mean by adapted, because generate could be in two different contexts. Because in group theory, when you say a set generates a group, you automatically include the inverses. You add the inverses to the set. And what we mean here is generates as a semi-group, meaning that if you don't have the inverses to begin with, you don't talk about, because then, if you think about it, the random walk can't reach every place because it can't use the inverses. Okay? But when we're talking about symmetric measures, it's the same thing. It doesn't matter. So in the meantime, and you can get this, and we're always going to talk about symmetric and adapted probability measures. We're not going to talk about, unless we start doing real sophisticated things at the end, or if we do something different, then I'll try to be very, very specific about what the assumptions I'm doing on mu. And usually when I write G mu, I mean a symmetric and adapted. Okay, that's what I mean, symmetric and adapted. Okay, and now I want to put a little more conditions on mu because, well, because you need them, and also because I don't want to start from the most general mu. I mean, so one example which we already gave, example of a generating symmetric adapted measure is just you take some group generated by a set S, and S is symmetric and finite. Right? Finitely generated group with a symmetric generating set, and you just take mu to be the uniform measure on S. Then mu is symmetric because S is symmetric, and mu is adapted because S generates G, so S is exactly the support of mu in this case. And this is called the simple random walk. So this is called simple random walk on what? Topic. Yeah. So I'll write it, but I didn't define what this is, okay? Like Cayley and not Monicus. Okay? It's a simple random walk on a certain graph, which is called the Cayley graph, and I'm going to define what a Cayley graph is, but I didn't define it yet. Okay? That's just one example, but you can have many examples. And basically, I would be happy just to talk about these examples. Just simple random walks on Cayley graphs, okay? Problem is, we'll see, they're not stable under some natural operations that you want to do. You want to move from this random walk to a slightly different random walk or to a different group, and you lose the nice properties. For example, this property has that the support of mu is finite. You lose that property very easily when working with groups. Okay? So we'll see that in the future. So you have to be careful. I have to give more conditions on mu. I need mu to be somehow related to the geometry. Again, we wanted to tie three different things. Algebra. This is related to the algebra. You see, mu is generating by a group. The random walk is basically multiplying by independent elements from the group. There's some algebra going on in there. There's analysis because we have a random walk, a Markov chain. Can analyze it. It's an operator on the space, right? So we can analyze these things. And now we want to put in some geometry. Then we need mu to understand what's going on with the geometry. Okay? And then you'll see that because mu talks to the geometry and mu talks to the algebra, then the algebra and the geometry also talk to each other. Okay? This is a love triangle. Okay, so let's put the geometry on. So we can start with the Cayley graph, but okay, so let's talk about let's just define a Cayley graph. Definition: a G be finitely generated group and S a finite symmetric generating set. This says S is symmetric, this says S is finite, this says S generates G, right? Finite symmetric. Once you need two pieces of data, okay? Then define the Cayley graph of G with respect to S. Too many letters, so we denote it by K, Cayley, G, and S. You need these two things together. Talk about the graph. What is a graph? A graph is a pair of vertices and edges, right? So this is going to be, so we define it to be a pair. Well, what are the vertices? The vertices are just going to be G. Okay, so the vertices are just the elements in G. And now I need to define edges, right? Edges. Okay? Where the edge set here depends, of course, on G and S. Okay, it's defined by what are edges? Edges are sets of size 2. Sets of size 2. So an edge is going to be X and XS for all S in S. Now you must be careful here, because what happens if S is just a finite symmetric generating set, could possibly contain one, could contain the identity element, and then this would be a self loop. I'm allowing self loops, not going to go really into, they're not going to change anything that happens, okay?
You only care about right multiplication, right?
Yeah, so it's right multiplication. You can ask, why is this an unordered pair? Well, it's an unordered pair because S is symmetric. So if you look at X and XS, it's the same as looking at XS and XS, S minus one. So, okay.
No, but what I meant is, we're not talking about left multiplication, right? It's just like a right.
Yeah, so yeah, it's kind of standard nowadays to always look at right Cayley graphs. You could define left Cayley graph, there'll be kind of the inverse map will give you an isomorphism between them. They're isomorphic as metric spaces, or isometric as metric spaces, or isomorphic as graphs. And but we'll always talk about right. There's no, I mean, if we do one, it's just convention. So this is a Cayley graph. Now, a Cayley graph gives you a metric, okay? Note that there is a graph metric, right? Just distance between any two vertices, and the distance is just the length of the shortest path between any two vertices, right? And this graph, by the way, is connected. This graph is connected because S generates G. So from any X to any Y, there is a sequence of multiplications that will get you from X to Y, right? Because we only need to generate the element X minus 1, Y. Okay, so this is a connected graph. And maybe we should write that. So S generating G implies that the Cayley graph is connected, which is the same notion of connectedness as a network. When we view it as a network, the conductances are one. It's exactly the same thing. A network with one conductance is a graph, right? So you can think of it as a network. It's the same notion of connectedness. Okay, so the fact that S generates means that the Cayley graph is connected, and note that there is a graph metric, ds. You can write ds, or sometimes we can write it dgs. Sometimes just write dg, depending on what we want to stress. If we have different groups, different generators on the same group, or maybe different groups with different generators. Okay, and some we just write d. Okay. But also, so this is just the distance, the graph distance. So dxy will be just the graph distance between x, y. So for example, if x is equal to y at 0, if x and y, if y is x times s for some generator s, then it's 1. And if it's longer, right, if you have to find the shortest path. So you have to minimize over all possible finite paths.
It's just the length, the word, make x or minus 1 y, right?
Such that xj plus 1. Look at all possible finite paths from x to y, and you take the minimal length of such a path. Right, it's a graph metric, okay? So now, easy to note that this metric is left invariant. Metric talks to the group structure. Okay? It's coming from a generating set, left and right multiplication. So, so it's easy to prove this. Okay? Take a path between this and this, and you show that it's a path between that and that. You don't have to show an inequality because you can always multiply by the inverse. Okay. So you can check that any path from here to here, length n, is also a path from here to here of length n. So this means that this one is at most this one. That's enough to prove that they're equal.
Not the same path, but just like labeled.
Well, any path you have in that one, you can get a path for the other one, of the same length. Okay, so I'm not going to do that. That's it. So we use the notation, and it's much so in fact, the graph distance is given by a norm. Cayley graphs given by a norm. What is a norm? Norm is just, well, it's what you think it is. So, and in this case, the norm would be, I would write x sub s, and sometimes I leave the s out, or I write g if I want to stress again, like before. But xs, this would just be the distance from s to the identity element. And now this is going to satisfy a few properties, right? Going to satisfy one, that it's a non-negative number. This is always non-negative, and equal to 0 if and only if x is the identity, right? E is a metric.
And we don't have
Okay.
one in the S. No, sorry. That's not sorry.
Minimal path.
Yeah.
2, I mean, this is an honest to goodness metric. Doesn't matter if you have one or don't have one. The self loops will not change the metric because they can't make paths shorter. They can only make them longer. If you take two elements in the group and you multiply them and then you take their norm, then what you get is that this is at most the norm of x plus the norm of y. This is the triangle inequality. Okay? And the third is that this is a symmetric norm. Now, any left invariant metric, left invariant in that sense, for the diagonal operation, comes from a norm, like that. And any left invariant gives you a norm. So basically talking about norms or left invariants is the same thing, okay? Sometimes people like norms that respect conjugation. This does not respect conjugation. Careful. Does not respect conjugation, okay? But there is this notion of norms, but we'll use this notion. Now, many times I'll write this, okay? And then what happens is that actually the distance, this distance, if I use this notation, then the distance between x and y is just the norm of x minus 1y, which is also the norm of y minus 1x. But be careful. This is not necessarily equal to the norm of xy minus 1. That is wrong. Okay? Be careful how you do the minus ones here. There's not an abelian group, not necessarily an abelian group. Okay? This is some kind of commutativity relation. Not always true. So this is the distance from x to y or from y to x, but this is the distance from x minus 1 to y minus 1. That's a different pair of verses. So we put the geometry.
The metric is left invariant, but not right invariant.
Yeah. You would do a left Cayley graph, you would get the opposite. It's important if we do the convention that we have a right Cayley graph, we have a left invariant metric. We'll soon see how we do harmonic functions. We'll also have a choice. Okay. This gave us a geometry, and now I want an assumption on mu. And the reason I'm making these assumptions, is because I know that we will need them later on, okay? Not just to have general conditions, but I know that we will need them later on. So definition. So let U be prob G be a finitely generated group. Okay, fix a finite symmetric generating set for G, S, G. I could have said fix a Cayley graph, Cayley GS, and then you know that S is a finite symmetric generating set. Like maybe I read it that way so that you fix some A S. So this means that S has to be a finite symmetric generating set, right? If I told you it's a Cayley graph, that's fine. So you fix it once and for all. Okay, I'm going to define the definition. It doesn't depend on S. So at the end of the day, we have to show that it doesn't. So the definition that if you take two different S's, you still get the same conditions. Okay, so definition. Fix a Cayley graph. So we said what mu is symmetric, right? That has nothing to do with S. We said what does it mean for mu to be adapted? That doesn't have anything to do with S, just support of mu. And now I want to define mu has kth moment, or K is some, it could be any, it could be any real number, but we'll only think of positive integers at best. So K could be any real number. Okay? So mu has a kth moment if when we can take the expectation, according to mu, okay? So we take a random mu element, okay? Let's call it x1. So x1 is a random group element that is whose probability measure is mu. Okay, so the law of this element is mu. The probability that x1 is equal to x is mu of x. I'll write that down in a minute, but I'm just explaining what I'm doing. Now I cannot take expectation of a group element. There's no such thing. Expectations work on real valued random variables, right? Maybe complex, but not anything else. So I need to make this into, I need to take a function of this. The function I'm taking is going to be the norm with respect to S. Okay? Now I have a real valued, in fact, non-negative number, so I can take expectations, right? Not this, but I put a little k here. With negative, positive, zero, I could do whatever I want, right? This is a real valued object. You have to be careful if you put a negative k here, what happens when this is zero, but okay. I'm not going to worry about that for the moment. Think of positive k. Okay, anyway, we don't care about that. Negatives won't give us so much information. Okay, this is a well-defined expectation, and I want this to be finite. Could be infinite. Could be infinite. I want it to be finite. Okay, if this is finite, then we say mu has kth moment. You can notice that if you have a bigger k moment, then you also have the smaller k.
Yeah,
Okay.
and you want to say that it's not independent of S?
I want to, so at the moment, the definition depends on S,
Yeah.
but I said mu has finite kth moment, and I didn't say with
Yeah.
respect to S.
There's no S in the definition.
So we have to prove that our definition is good. I could have said with respect to S and then said, oh, it doesn't depend on S, but you see it from the definition. This is one definition. Second definition is mu has so mu is smooth. Sometimes we say exponential moment. So, yeah, I don't know. I invented this name, and people, this is, I also invented this one, but well, people say different things. It's less standard. I thought that this would be better than that, but okay.
Moment comes with doesn't moment come with the exponential? Normally, like in.
Yeah, so there is a thing, but you have to understand what you mean by exponential moment. So mu is smooth, exponential moment. Sometimes you would say here exponential tail. There are different things. I didn't say what x1 was, so in a minute, okay. Mu find in a group, and here we'll say what x1 is. So let xt be the mu random walk. Okay, so what does it mean? Xt is multiplying t independent mu elements, right? And x0 comes from some distribution. So what is x1? X1, when I don't put anything here, right? It means I have the random walk started at the identity, and I just multiplied by one mu independent element. That's why I wrote it x1. It's just a one jump of the random walk.
But does that mean mu independent element?
So the random walk, remember, what is the random walk? The random walk you start, so x0 has some distribution, right? And then xt is just x0 times u1 up to ut, where uj are iid mu. Right? All independent, same distribution mu. So x1 is u1, at least if you start from the identity. When I don't write, remember when we write e sub nu, then we mean starting from nu. When e sub x means starting from delta x. E sub nothing is starting from just the identity. Okay, so that's the convention. So what is exponential tail? Exponential tail means that there exists some epsilon such that the expectation of this guy times epsilon exponentiated is finite. This is a much stronger statement than any of these. So this implies this for every k. Why? Because if you write this out, if you expand it as a power series, right, and you'll see that they all have to be finite. If one of them is infinite, this will explode. Right? In general, this is just a statement about non-negative random variables. But so that's what those are the conditions we're going to work with, and we're basically going to write. Notation. This is the notation I invented. But since I might outlive some of the people who have different notations, then maybe this one. Well, anyway, in this course, we're going to use this notation. S, A, G, K is the set of symmetric, adapted,
So it's in the book where I was reading.
probability measures. Well, again, it's my notation. So
Yeah, no, I had to go to the index key and look for it.
So a set of symmetric adapted probability measures. Well, there's a list of notation. You just click your jumps.
That's what I did.
With kth moment. Okay, so that's what the k tells you. If I tell you mu comes from this set, then you know it has a kth moment. And when I write infinity here, is the set of adapted probability, symmetric adapted probability measures with exponential moment. Or smooth. Okay? That's it. Infinity just means, infinity could a priori mean that you have kth moment for every k. That's not the same as having an exponential moment. That's weaker. Okay? Having something for every k does not mean that you have an exponential tail. But, and I can easily give examples. These things basically don't have anything to do with it.
So you don't use anymore the notation SAS?
No. But because in the book I wanted to, there's some statements about kth moments and some about exponential tails, and I didn't want to confuse the. So when I put infinity, I don't mean just for every k. So this thing is strictly bigger than the intersection of SA GK when I run over all k. Strictly bigger.
Need to use omega instead of infinity. Like you have C infinity in
Check it.
functions and C omega is analytic.
Yeah. Okay, and it's easy to see that if you have a symmetric adaptive measure with if you have k, so if you have k plus 1, then you have okay, this is what I said. I mean, this is just Jensen's inequality. Okay. Good, so we have the structure that we want. Take a break. Okay, so we take a break and then we talk about gradients and divergence and Laplacians. We do some discrete analysis, okay? So let's start doing discrete analysis, okay? Have all the structures in place, especially networks, because we're doing analysis. So we want to tie the geometry and the analysis together. So we'll do something about networks. So let's look at some spaces. So we start, our basic geometric structure is a network. Start with a network and we define spaces on this network. So GC is a network. Connected network. Okay, from now on, right here, connected. And from now on, whenever I say network, I mean connected network. So if I want it not necessarily connected, I will specify. If I forget to say connected, I meant connected. Okay? So connected network. We can look at a few spaces. First spaces we can look at is little l e GC. What is this? This is the set of all functions from G to the complex numbers such that the P norm of F is finite. And let's say what the P norm is. Okay. So first, let's do P, which is between 1 and infinity. Okay. The reason I'm not doing, well, okay. 0 and infinity. When P is smaller than 1, it's not a norm in the sense of a norm of the actual, Banach. So you have to be careful. But I can define this number. So the norm of a function, P norm of a function, to the power P is just the sum over all elements in G. You take f of the element, you take absolute value, and you put a little p. Right? So root p of this thing, and you all have met this object, right? Okay. The reason I don't have to worry about measure 0 and anything, right, is because my set is countable. Measure 0 just means, the a priori measure on the space is the counting measure. So measure 0, it's just endless. Okay, so it's just honest to goodness functions, not modulo measure 0. So that's the norm, and this is, so LP is a Banach space. Don't know what that is, it's not so important. Or P greater or equal than 1. Okay? I didn't say what infinite and 0. Okay, so Banach just means it has a norm and it's a complete metric space. Okay, and the norm induces a complete metric. Okay, Right? It's a Banach space, right? You all have, who hasn't ever seen the LP space? Never. You've never seen?
Never. I've seen. I think I saw it. Modern mathematics.
Especially important is L2. Especially important is L2 because this is a Hilbert space. What is a Hilbert space? It means means the norm comes from an inner product. Okay, it's a Banach space such that the norm comes from an inner product. We'll see it. Well, I'm going to elaborate a lot on that. Okay, so the importance of L2 is that it's self-dual. So it's a Hilbert space. Okay. Okay. What about the infinity norm? So the infinity norm, I'm sure you've all seen. Infinity norm, this is just the maximum or the supermom, sorry, supermom. Say supermom. Look, these things could be infinite, okay? They're well defined even if they're infinite, but they could be infinite. We take only those that are finite into our space, right? So this is the supermom over all x and g of the absolute value of fx. Again, f could be negative, could be, in fact, not, it could be complex. So the absolute values. These are all vector spaces. This is also a Banach space. What about zero? What is a zero norm? You know, you think about limits.
It's just the support.
Think about what you're doing, take limits of these things. It's just a support. Size of the support. So it's the size, absolute value of a set, or let me write number. Number of a set is this number of elements in that set, including infinity. Okay. So it's the size of the number of elements in the support of f, which is just the set of all x and g, such that f of x is not equal to 0. 0 is special. 0 is special. Okay, even the complex number, 0 is special. Okay. So this does not mean there's a size of the support. Okay. So L0 means that
Finitely supported
finitely supported functions. Now, what I wrote here is that I cheated. I misled you. Didn't cheat, I misled you. Because you're asking, why did you put a C inside? Why did you put a C? Why did you put a C? So here, I don't need the C. This is actually fine. Well, not exactly. I do need a C, sorry. But here I don't need a C. This will still be finite. But now what I'm going to do is I'm going to plug in a little C here. Cx, remember what, if you have a network, Cx is the total output from X, right? Total conductors from X. It can change, right? These Cx's, I never said they're bounded. If we have a network coming from a probability, symmetric adapted probability measure, right, then they're all 1, so we didn't change anything, okay? But if we have a network, more general type of network, these can get bigger and bigger. Think of a graph with unbounded degrees. So the functions in L infinity will no longer, if I put in this weight, this will still be a Banach space. The ones with finite L infinity norm will still be a Banach space, but it will not necessarily be the same space as L infinity without considering this changes. Changes the space. It's a weight function, yes. These are all always positive, right? You could do it with any sequence of positive numbers. This will always be a Banach space, okay? Similarly, I'm going to put a C here also. Okay? I put these weights. And now, first of all, C is important, but the statements remain correct. Both that this is a Banach space and that L2 is a Hilbert space. Okay? So it's important to put the C's in. Why? We'll see, especially for the Hilbert space. Okay? This is the thing we want to work with. And since the Hilbert space is important, then we have some notation, confusing notation, because I know what norm 2 is, right? I know what the 2 norm is, right? Now I'm going to write the C norm. See, if C was a number, if C was, I don't know, 1.32, right? This would be the E equals 1.32 norm. But now C is not a number, C is a conductance, it's a function on a pair, right? So when I put the little c here, what I actually mean is the 2 norm. Okay, but the 2 norm with respect to C. See, because this notation, see, I misled you before, I wrote P and, now you have to remember in that notation, oh wait, which C are we talking about? Are we talking C constant 1? It still makes sense, even if you have a network. It's just that it doesn't look at the network itself. These guys, when I put the weight function, the proper weight function inside, they look at the network. There are some papers which start doing this with a general network and a general weight function, and then you have to have some connections. For example, you have to have that somehow the weight function has some connection. Okay, so the weight function has to have some connection. Ratio between the weight function and the C of x's has to be bounded below and above. Uniformly in X. That's usually a condition that people, but I just find it to say the weight function is the conductance function. Okay, so that works best, and we don't want to generalize just for the sake of generality. Okay, now let's define a few things. I remind you of the notation. Another notation is that I write E of GC. Okay, this is the set of all pairs X, Y. This is ordered pairs, such that CXY is positive. Now, so this, what it does, is it looks at the edges in the network, and it takes each one of them twice, one in each direction. Okay. So I just use this notation. It's just easier to write this than to write every time I go over all pairs, such that CXY is positive. But what you need to remember that for each pair, you go over twice. If I sum over all these things, I'm going over each pair twice. Okay. Okay, good. Well, I'm going over each pair twice for the pairs that are, it's not XX. You could have conductance, it's like self-loop movements. Okay. Yes, what did I want to do? We have our L2 space. I told you they're Hilbert spaces, so let's see what is the Hilbert space. So L2, so this is a fact. L2 GC is fact. Is a Hilbert space with inner product given by, right? So a Hilbert space is a inner product space. It's a vector space with an inner product structure such that the inner product induces a norm which gives a complete metric. Right? That's the only other thing. So, and this is true in general for general weights. This is just this is just a fact about weighted norms and sequence. So you take general weight function for sequences. Okay? So L2 is a Hilbert space with inner product given by, so the inner product between two functions, right? So F and G. I know I use G for green function, but now it's not the green function. In the notes, they look different, a different font. But I'll try, maybe from now on, I'll try to write green function. We'll come back to the green function, and I'll try to write green function, something like that, just to make sure that you understand that it's a green function and not the. But here it's just general F and G. So if you have F and G, I put a little C here to remind us that we're taking inner product with respect to C, not just any inner product. If C is identically 1, then it's the usual inner product, and you just integrate, which means in this case sum, right? You take F of X, take G of X, you complex conjugate G of X, complex conjugate, these are complex valued functions. Okay, this would be when C is X equal to 1, and you put a little weight here. Okay, this happens to be a Hilbert space. You have everything, you have Cauchy schwarz. If you take F equals G, you get the norm, you get the 2 norm. So this is an inner product, but we can also look at functions of the directed edges. We can also look at functions of the directed edges. We can also define for f and f tilde, which are going to be functions from E, G, C to the complex numbers. So what does these functions take an input, a pair, okay? And they output a complex number. We can define an inner product little c here. The notation is the same, but it's a different inner product because it's living on a different space. And these are not functions from G, but these are rather functions from the edges or the directed edges. Okay, and we define this inner product to be the following. Sum, this is going to be very, very weird. Okay, what do I need to sum over? I need to sum over x pairs xy. Where do these pairs live? These pairs live in EGC. Okay, that's one thing. Second thing is I want to take f of xy. This makes sense because f is a function from the edge to complex numbers. I want to take f tilde of xy and complex conjugate it, right? This is the general structure of an inner product. And now I'm going to divide by cxy. Very important that I divide by cxy. Not multiply, but rather divide. Why? Because I do a lot of research and you realize that this is an important thing to be right. Other? Okay, what is 1 over conductance?
Resistance.
And it's a resistance. So this is the space that has to do with resistance, not conductance. You see why I have to sum over these guys, right? Because I can't write this. No resistance, there were infinite resistance if I. Okay. Then, this space becomes a Hilbert space as well. Okay, so the fact, I'm not proving these facts. These are general facts you can even try to think of how to prove them. General facts about random, about arbitrary weight functions of this type of, you always sum function against its complex conjugate, and you could put a weight, positive weight. That's all you positive weight. That's.
We're gonna sum each.
So 1 second. So L2 of EGC. So L2 of GC is just that space. L2 of EGC is going to be the space of all functions complex valued such that their C norm is finite, where the C norm, of course, is the norm induced by the inner product. Okay, so the C norm of a function in this space is just the sum of the resistance times the function absolute value squared. Okay? Just f equals f tilde. So, and this, and the fact is that this is a Hilbert space. The fact that these are Hilbert spaces is not so important for me, more than they just to verify that it defines an inner product and everything it works well. Okay, honest to goodness inner product, not semi-inner product or not semi-norm or anything, right? Just the only functions that have norm 0 are the 0 function. Okay? Good. So now I'm going to define operators. Okay. I'm going to define operators. So we take some function, complex valued, and we take some function of edges, complex valued. Okay, still working with GC being an input, everything is. We're going to define operators from the set of these types of functions to the set of this type of functions and the opposite. Okay? So I'm going to define this nabla f, gradient of f. Okay? Find the gradient of f. The gradient of f is going to be a function on edges that gives me a complex number. So if f is a function on vertices, this is a function on edges. So the operator nabla takes f to takes a vertex function to an edge function, maps one space to another space. Okay? And I'm going to define a divergence of big F. This is going to be a function from G to C. So it takes an edge function to a vertex function. So you cannot write nabla of nabla, right? You cannot compose nabla with itself. You cannot compose divergence with itself. But you can compose one on the other. Right? You can go from a vertex to an edge and then back to a vertex function. That's what you get. You can ask for the opposite. What? No,
No.
no zero. Not zero. We'll see what you get. Yeah? We'll see. We'll see. Yeah. Next question? No. So how do I define it? Well, so this is an edge function. I have to tell you what it says on an edge, right? So I define this to be, it's take the conductance and then take the difference. This is a gradient, right? So you take the difference with the edge weight. Okay, think of this as the analog of a gradient of a general function. Okay, and of a derivative. There is a choice here if you do f of x minus f of y or f of y minus f of x, but anyway, we define it this way. Okay. I want you to notice that when I switch x and y, this is not a symmetric function at all, and I never assume that these functions are symmetric. I'm taking directed edges, right? Not undirected edges. They can give different values. This gradient, if I reverse the direction of the edge, I also reverse the sign of the gradient, multiply by -1. Okay, it's very important. Okay, and the divergence of this is a function of vertices, right? And now it's a complicated function again because I have to do with this. I'm going to sum over all y such that xy is an edge. I'm summing over all the neighbors of x. Okay, could be infinitely many of them. I'm going to divide by the total output from x. Okay. And then I'm going to take f of the edge xy minus, so the anti-symmetric version of f. Anti-symmetrizing f. And sometimes some people would say that you want to divide by 2 here because you've taken f twice. Right? I'm not going to divide by 2, but the 2 will come up in other places. So, you know, it's a choice where the 2 comes up in. Right? I mean, many times in mathematics, you know, you have a 2 that's playing a certain role, and if you don't put it here, you have to get it somewhere else. So maybe some people would have defined this with 2 here, denominator, because you have. And it's very interesting because, okay, let's do a theorem. Let's prove something about these things. First of all, an exercise for you guys to verify. So this is everything here is well defined. Well, maybe this is not really well defined if you have to be careful about infinite sums here. Okay, for general functions, but so I know I could say this is defined if the sum converges or whatever. This is always well defined. This has no problem. But exercise. So just prove that nabla is an operator that takes L2 functions. So it's well defined and takes L2 functions to L2 functions, but of course on the corresponding spaces. Okay. So this means that if you start with an L2 little f, you get an L2 in the other space, in the space of edges. You have to verify that this works. And div, the divergence, this takes an L2. And if I write that it's a function from this, here you also have to verify that it's always well-defined when this guy is in L2. Kind of already see it. I mean, you basically split this into two sums and you can bound it by sum. Okay, so sum will converge. Guaranteed to converge absolutely, in fact, if you're in L2, and it takes an L2 edge function to an L2. That's a separate statement. So first of all, it's well-defined, and second of all, the image of this function stays in, well, goes into the L2 of the vertex space. Okay, so these operators at least are nice on the L2 spaces. You can ask what they do in larger spaces, and we will talk about, in some sense, about these operators on larger spaces, but through a different prism. Not completely, okay? So, good, so let's do a theorem. This is sometimes called integration by parts. Why? Well, I don't know. Well, I do know, but I don't know if we should have a discussion. Integration by parts says that if we have F L2GC and big F in L2EGC, okay, then we can look at the following thing. We can look at F inner product with nabla F C, right? This is a well-defined thing because I took the inner product of two edge functions and they sit in L2 by the exercise, right? So this is a well-defined number, complex number, okay? And it happens to be equal. This is equality in complex numbers to what?
Again,
I want to put this F here. But then I can't put a big F here because that's lives in a completely different universe. But I put divergence here. They are dual operators, yes. They're adjoint operators. And when you have between Hilbert spaces, it's an adjoint. Okay, so the divergence and the gradient are adjoint operators. Go from L2 to L2, two Hilbert spaces, and they're adjoint. And this is very useful to remember this identity because it gives you a lot of shortcuts. Now we're going to prove this identity by getting our hands dirty, just brute forcing it. Okay, there's some way to look at these things in cohomology and homology and cohomology and chains and anti-chains, and we didn't even know where to begin. But we're just going to brute force these things, okay? And show this identity brute force. But basically, once we do brute force, we don't need the brute force anywhere else. We can just write everything. If we know how to write things in inner products, we just remember, oh, I move it around, it becomes it. Very easy, okay? Good. Proof. What do? We need to compute things, right? We need to compute things. Okay, so we start with the left-hand side. Should we start left-hand side, the right-hand side? What do you want to start with? Okay, let's start with the right-hand side. Divergence FC equals to sum over X, right? This is how do we take inner products? We sum over X, multiply CX. Now, look at the functions, right? Divergence of F. What is divergence of F? Divergence of F means I sum over Y such that XY, let's write CXY is positive, right? That means Y is an edge. Sum over all the Y such that CXY is positive, right? I do 1 over CX, and I take F of X, Y minus F of YX, right? That's I just erased it. Okay, so this is F of XY minus F of YX. Okay, all of this thing, this was just, okay, I just plugged it in. Now I plug in F of X complex conjugate. That's it, okay? Now, what do we want to do? Well, first of all, C of X cancels, right? And now we want to look at we have two sums, right? So what are we summing? So what are we summing? What, when we cancel the c of x, we have sum over all the x's and all the y's such that cxy is positive. That's the same as just summing over all the x's and y's such that cxy is positive, right? So that's just summing over all the pairs, ordered pairs, because x, y, right? So this is the same as summing over all ordered pairs inside EGC. And then we have this, we have that I want to do. Yeah, we have f of xy, right? Now, I know that this sum converges absolutely. I know it because it's an L2 space. I know the sum converges, I can manipulate sums. Okay? I mean, you have to convince yourself that each of these two separate sums converge absolutely. So the difference between sums is the sum the sum of the differences is the difference between the sums. But I'm leaving this detail for you to verify. So I have f of xy times f x complex conjugate. Okay. Minus this same thing, f of yx times fx conjugate, right? Now what do I do?
We try to work with the other.
Well, now you see I have the two sums, they look the same, but you see, so always change your variables so that you want to work with the other guy. Here, I split this into two sums because I had fx and fx, right? But now I want this guy to be the same. So what I do is I replace and I use the symmetry of this condition. Instead of summing over xy, I can sum over yx. What happens when I sum over yx is that this becomes f of xy, and this becomes f bar of fy, right? Because this one has to go with the second one appearing here, right? It's the same sum, but I just reordered the sum in a different way, okay? And so the whole big thing, now I put them back together again, the whole big thing comes out to be sum of xy in EGC. I have f of x minus f of y, all of this, complex conjugate, and I have fxy, fxy. I need a bit of room here, sorry. fxy. This I have, right? This is the sum. And now this is not exactly what I wanted because I wanted to see a gradient, right? And also this isn't the correct inner product. The correct inner product is to put the resistance here.
Multiply by.
So you multiply and then you have the gradient. And I can do it because I'm only summing over the guys in the edges. So this is exactly what I wanted. This is exactly, so the resistance, the 1 over conductance gives me the correct inner product. And the inner product is between, I look at what the functions, there's an f here, and in the complex conjugate, I have the gradient of it. Okay? The conductances are real numbers, so complex conjugate doesn't do anything. Okay? So this is the correct, right? This is what I wanted. Make sure I didn't lose any complex conjugates. F stayed on the left-hand side. Good. So this is a theorem. And a theorem. Okay? Definition. Why is this? Okay, why is this integration by parts? What happens when you think of the real value, Rn or something, right? You have vector functions on Rn, maybe complex value functions on Rn. What does it mean? This is integral of f gradient f, right? This is integral of the divergence of f, right? Forget the bars, but I mean, bars. Okay, right? Now, these live kind of in different worlds, right? But there are theorems relating them. There's boundary conditions, right? You have to put them in the domain. There's a boundary. But if you think in our boundary, where's our boundary? It's at infinity. The functions are going to zero in infinity because they're L2 functions, right? So we kind of have, you can imagine you have some kind of boundary at infinity, whatever it is, right? The functions on the boundary are going to be zero because, if they're in L2, they have to decay when you go far away. And then there's no boundary effect, so these things just become equal. Okay, if you can find theorems in Fish-Shalosh, I don't know, right? That are correspond, or maybe Alba.
It's sort of
Corresponding. Yeah, it's a relative of Stokes. So it's a kind of discrete version of Stokes, or I never remember if it's Stokes or Green, or and probably somebody, a third guy even
All of them are still.
was the first one to prove them, was probably even somebody else, but or maybe probably Green. Actually, probably Green was the first. I mean, Green understood all of these things.
Green's identities.
What?
This is one of Green's identities.
Yeah. So
Not
Green.
exactly Gauss or Stokes. So
Yeah. So I think Green was the one who really understood these things in the Euclidean setting. Then you have Riemannian manifolds, and you have like complete. You can go all the way up to Minkowski and Einstein, and like so these become completely terrible. Here you see it's just like I just did one brute force calculation. I get it. It's not really difficult. Okay. Definition. And what happens when you compose in real life? What happens when you compose gradients and divergence? Then you get the Laplacian. You just have to look at. You have to think of what it means to compose the operator, which is the gradient. So the gradient is giving you the vector of the partial derivatives. Divergence is giving you the sum of the partial derivatives, right? When you compose these things, it's just giving you the inner product between the partial derivatives, sum of partial second derivatives, right? Which is the Laplacian. So in the Euclidean setting, the Laplacian is the composition of these things, and we're going to get a 2 here. And the 2 is coming from the fact that I didn't put a 2 in the other definition. It was complicated enough. Okay, so you put it in one place, you don't get it in another, and in the real case, things are different because it's integrating. So, but up to this little 2, this is exactly the same phenomenon. So definition. You can define an operator, which is, so let's define it's going to be from L2 GC to itself. Okay, takes an L2 function to an L2 function. Okay, and this operator is going to be, I have to tell you what it does for an L2 function. I don't need to write it like this again. Don't need to write it like this again. It's just the operator is. So I want to go from L2 to L2. So what operates on L2? This is nabla, gradient. Then I can operate, now I have edge function. What operates on edge function? Divergence. And I take a 1/2 here because I told you I was missing the 1/2 in the divergence. So you can think of 1/2 divergence as the actual divergence, or think of it any way you like. This is just the definition. This, we proved, or I gave you an exercise to prove that this takes L2 to L2, right? Because this takes L2 to L2 edges, then it takes L2 edges back to L2. And again, cohomology, cochains, and chains, you know about these things, then this has something to do with that. Okay, Laplacian. Second definition. How do we define a harmonic function in classical analysis? Function that zero has a zero Laplacian, right? That's one way to define a harmonic function. Okay, so for a function from G to C is said to be harmonic at X in G if Laplacian f at the point X. So I take the Laplacian of f at the point X and I get 0.
So you assume that f is in L2?
Good question. No. Need to show why the Laplacian is actually good without assuming that f is 0. What we know for the moment is that it's always well defined on L2. But I'm going to extend the definition because we're going to give us, this was a motivation. We're going to give a separate definition, it's going to coincide. Okay? So it's harmonic at X, and f is harmonic in general Now, I want you to notice all these things depended on a specific network, so they depend on C. And if it was a C coming from a mu, from a random walk, this will depend on mu. When we get to the mu's, we're going to say mu harmonic. Mu harmonic means it's harmonic with respect to the specific probability measure inducing specific network, inducing all of this structure, okay? Because we might want to say mu harmonic and mu prime harmonic. In fact, one of my favorite open problems has to do with the relation between mu and mu prime harmonic functions. How do they talk to each other? How are they related, if at all? So now I'm just saying harmonic, but under the carpet, there is a C in the background. So we have to remember that there is a C in the background. F is harmonic if the Laplacian of F is identically zero. Okay? Now I want to extend this definition to non-L2 functions. In fact, exercise. So you'll see that in a minute. If I want to talk, if I would stay in L2, this would be boring. It would be boring exercise. Show that if F is in L2 of GC and the Laplacian of F is, so this is well defined for that. So if the Laplacian is identically zero, meaning F is harmonic, then F is constant. And in fact, if G is infinite, then the only constant function in L2 is zero. There are really no L2 harmonic functions. Right? So no L2 harmonic functions. No, there's no, I'm leaving this for you as an exercise, okay? You could have constants if G is finite, because then it's just, then any function is L2. Okay? Hint, use integration by parts.
Move the again. Here.
Well, we want everybody to have fun, right? This, by the way, this fact that no L2 harmonic function in classical analysis is not a trivial fact. I mean, the proof is not like two lines like here. Here it's two lines. You integration by parts. Well, use Stokes theorem there or Green's identities or something. You also get the same result. But there you have to be careful because there are zero boundary conditions. All these things in the Euclidean space, you're working in certain certain domain. Be careful.
Is the definition in general equivalent to the one where you have the like the integral?
Yeah. We'll soon see the mean value problem. We'll see it pops out. Pops out of the definition. So I'm done. Okay, let me just 2 more minutes. Okay. If F is in L2, what is the Laplacian of F? Let's compute. At a point, I didn't say it's harmonic, then it will be 0, but maybe it's harmonic at X or something. What is the Laplacian? Okay, so it's 1/2 divergence of nabla of F at X. This is a very quick calculation. 1/2 of what is the divergence of a function? So we take the function at xy, we take the function at yx, right? Let me put the 1/2 here. Okay. Okay, that's what we do. Then we have to sum over xy. And we have to do a resistance, right? No, we have to do a total weight. Sorry, what did I do? This is at x, summing over y such that cxy is positive. That's the divergence. Divergence of this function. Gradient. But now, gradient is antisymmetric, right? Gradient is antisymmetric, we already noticed that, right? So gradient xy minus gradient yx is a gradient xy. You have 2 of them, and you divide by 2. Okay? That's why you want to divide, right? So what we get here is we get the sum over all the y's such that cxy is positive of what is the gradient? It's cxy We have the Cx that we had from there. And here we have f of x minus f of y. Now, if you notice, I can remove the Cxy positive because if it's 0, it just kills this. I'm just summing over all the y. What is this? This is, to notice, this is what? Sum over all y, pxy, the p coming from the transition matrix of the random walk. Okay? This is true for an L2 function. I didn't. Okay? Transition function coming from the random walk of f of x minus f of y. Now, this could maybe not converge. These are complex numbers, maybe they doesn't converge. But if it does converge, then I can give this operator, this is an operator. I mean, we see what it is, right? So what we can do is we can extend the definition of a harmonic function, and we see what the Laplacian does at every point. Okay? Now, the sum over y's of p is 1. So this guy just becomes f of x. But if you want, it's the identity operator times f of x, right? So this becomes identity f, this is identity operator on functions, okay, at the point x, minus, when I sum a matrix times a vector, right, that's just matrix multiplication. We talked about this. So this is just pf, p operating on the vector f, right, at the point x. And if you want to write it, you can just write it as I minus p, this operator, f x. This identity, I use the fact that these sums converge absolutely in order to separate and put back together. Okay? Otherwise, I would have to be careful. Why does this sum converge? Why can I even speak about this sum? Okay? So what we'll start, the next thing we'll start is what we'll see that it's actually better to define this operator. A well-defined operator, and it operates on a broader space than L2, right? It operates on a broader space than L2. Specifically on L2, it coincides with 1/2 divergence gradient. Okay? But now, this thing is just an object in itself, and we'll see how this is basically, I just showed you the mean value problem, right? The average of f around the point is equal to f when it's harmonic. Okay, so that's how the mean value. Okay, good.
Thank you.